All right, so today we're going to have a very basic lecture on the introduction to data science and machine learning. I'm going to be talking about very basic concepts in data science and machine learning. Okay, today in this short lecture, what I'm going to be talking about is an overview of introduction to data science, and we'll cover some of the very basic concept in machine learning, and we'll talk about the linear regression and logistic regression. And there's a book that I usually recommend to the people who just are starting out in the data science and machine learning. That's a data science from scratch. But there are lots of other books as well that you can follow, read, learn. But this is just one example or recommendation of book from my side. Okay, so what's exactly the data science? The purpose of the data science is we design an algorithm, a process, a pipeline that we can use and extract a knowledge from some sort of data. That data could be structured data, or that data could be unstructured data. And data science is a mix of concepts and models and mathematics pipelines from three main domains. One is statistics, machine learning, and the computer science. So it's a mix of these three things. Sometimes you see we use the concepts from mathematics and machine learning, and then you apply them using the computational algorithm, using computer programming languages. So the main focus is extracting the knowledge and extracting some insight from any type of data. So that's the main purpose of a data science. And machine learning is one of the tools that we use in a data science. So now the thing is, now why do we need data science, or why do we have this domain, or why do we need these machine learning or computational algorithm to extract some knowledge or insight from a data set? So the reason is, in olden days, we have small data sets. We used to have Excel sheets. People used to have the record on the paper. So it was easy to extract knowledge or see some patterns in the data. But now we know that over 400 people use social media. That if we want to extract some knowledge, what the people are talking about and what are their sentiments about some topics. So data sets are huge. About 500 million tweets are discussed every day on Twitter, and that's just a Twitter. Obviously, there are so many other social media platforms. If we want to study some sort of pattern, we want to extract some knowledge from an airplane or aircraft. An average flight of aircraft generates about 500 to 1,000 gigabyte of data. So imagine it's a huge amount of data just in a single flight. So if we want to extract some knowledge out of this data set, normal computer algorithm will probably fail. So we need some sort of sophisticated method to extract knowledge from this huge data. Similarly, on YouTube video, if we want to extract some sentiment, some knowledge, if we want to target the plagiarism on the YouTube videos, these are just estimates, 30,000 hours of videos are getting uploaded every hour on the YouTube. So again, it's a huge data. During the COVID time, we've seen how people are expressing their sentiments. This is just an example where people are expressing their negative sentiments about the vaccine, and they're saying, "I feel fine. The vaccine didn't even hurt, but but the face looks like an alien." So if we want to extract this knowledge from an image, that whether the sentiments are positive and negative, so you see, it's a very hard or different domain which we human can do, but for computers it's a difficult task, and especially when we have millions and millions of tweets, images, videos getting uploaded onto the social media platform, then extracting that knowledge is very difficult. So the main reason we need the data science and these sophisticated algorithm, because the volume of the data is a lot, and the variety of data. From variety, we mean images, text, numbers, all sort of data type. So variety is increasing, and velocity, the speed by which this data is getting generating. We talked about 30,000 hours of video getting uploaded to YouTube. So volume is huge, variety, lots of type of different varieties available of data, and the velocity, the speed is average. So the data is exponentially growing. That's why we need some sophisticated algorithm to extract knowledge from this type of data. For humans, it's not possible. Even the normal algorithm that we used to have a few years back, they even fail to extract some knowledge patterns in this type of data. That's why there's always a need for people to tackle this type of huge data and this different type of variety of data that people can tackle. So usually a typical for in a data science, you have a research question. You want to know what are the sentiments of the people during the COVID about the vaccine. So this is an example of a research question. You go and collect the data, and many times we do the feature engineering. Feature engineering means you convert the data from one format to another format. A simple example could be you collecting the people's weight and height. So these are two features. So the feature engineering would mean that you calculate body mass index, BMI, from weight and height. So now you have a new feature in the data. So data scientists do a lot of feature engineering many times to give some meanings to the data. Then you apply different sort of machine learning model, AI algorithm, statistical model to extract some patterns from the data. Visualization is very important. We always visualize the data. What's the data look like? Now, what are the patterns? Because we human can visually see data better. We can see some patterns in the visualization. We do some final evaluation of the data, how good our models are for some sort of predicting or for some sort of extraction of knowledge. And then we'll see whether this model answers my original research questions or not. If it doesn't, then we continue. Well, after evaluating or after doing some visualization, now we might have more questions. So this circle continues. So we've used the machine learning in this short talk quite a few times. So what do we mean by machine learning? So machine learning are basically the mathematical models where we learn from the data. We develop a mathematical model, and we usually the way we divide data into two buckets or two sets. One is called the training data, and another one is called test data. So we could have, like, let's say 100 examples of a data set. These are the people. Some people have diagnosed with cancer, and other people didn't diagnose the cancer. And we could have a bunch of their different features, indicator, their age, their type of diet, their family history, or what sort of type of food they've been eating, whether they were smoking or they were taking the alcohol. So these kind of social indicators we have on people, and some of them are diagnosed with cancer and another are not diagnosed with that cancer. And now we want to see, can we develop a mathematical model that automatically can predict the people whether they have a likelihood of developing the cancer. So the way we're going to do that, we'll split the data into two buckets, into two sets. Usually the training set is bigger than the test set. Sometimes you take the training data, roughly about 80% of your total data. In some instances, could be 60, 65%. It's not like a hard and fast rule, but usually it's between 70 to 80%. In some situation, people use 90% of their training data. And then you show this full data set where you have all the features of people, and then you have an outcome. So you try to correlate, can we develop a mathematical model given these features? Can we predict an outcome which is whether the person has a cancer or not? Right. So once you came up with this mathematical model, then you apply this model to the unseen data, the data that this model has never seen before. We call it the test data. So now you only expose features to this mathematical model, and you will ask the model what's going to be the output, what's going to be the final result or outcome. And the model tells you whether the person will get the cancer or not. Then you compare those results with your original answer, because you have the answers right on this test data. Then you compare them together and see how much mathematical model was able to correctly predict these labels, right? So we've been using the word model quite a few times in the previous slide. What do we mean by mathematical model or just a model? So from a model or a mathematical model, what we mean, we want to learn this relationship where given some features, we conventionally call them X. So can we give a model some features X, and can we develop an equation where you calculate Y as a function of these input features? So this is the type of relationship that we don't want to learn for the training data, and then you apply it onto the test data, right? So X could be a single feature, or X could be many features. From feature, I mean a column in your data set. You could have a number of columns in your data set, such as what's your blood pressure, what's your BMI, what's your family history, are you smoking, are you taking alcohol? So these are your mm, input features. So that could be represented generally as an X or X1, X2, X3, X4, so on and so forth. Right. And Y is your output. In this case, let's imagine if we only have a two output, whether the person has a cancer, yes or no, or 0 or 1. 0 means you got no cancer, 1 means you have a cancer. So let's look at these two examples. In one example, we want to learn the classification. And another example, we want to learn the regression. So let's see what's the classification look like. I think there's some noise from the participant. So can we have people mute? Okay, now let's first look at what do we mean by classification. When you have some input data, um, your input features, that's refund, status, and income, and cheat is your outcome variable. So in this small data set, we're trying to see, given these three features, can we predict an outcome variable? In this case, the outcome variable are only two, yes or no. You got this person, he's refunded yes, we were single, his income was this, he cheated no, and so on and so forth. So when we have a discrete outcome for each of your row in the data, then it's called a classification problem. So again, that's your discrete outcome or that's your categorical outcome. When you have a number of fixed label, such as yes or no, or you could have a fixed categories, such as you might be predicting the type of cancer, whether you have in situ cancer, invasive cancer, benign cancer, or no cancer at all. So these, you got four categories. That means that's your four classification. So that could be a type of person. You could have a 4 or 5 type of person, or that could be a three-class problem. You got a Twitter, you tweeted, you have some features on the person, and whether you are a pro-vaccine or you are against the vaccine. So when you have a discrete outcome for your data, you have a or we can say when we have a categories for our data, then it's a classification problem. So in this problem, we want to learn, given that these three features, can we predict the outcome, which is yes or no. So the idea is when you have a new data coming in, we want to predict what would be the outcome variable, the cheat, yes or no. And the problem is, and that's where this mathematical model and the machine learning helps. The problem is we cannot make a if-else algorithm because this new data, our algorithm has never seen before. So if this is our training data, about this one is our training data. So if we try to look up a train in within the training data, whether we have a person with a no, yes, there are these three no's, and whether the person have a no, whether they are married, no married, no divorced, no single, yes, there's a one row with a no married, income is 80K, no, the income is not 80K, income is 100K. So you see, so now we have a test data, this unseen data, where we don't have an exact row in our data set. So we cannot do a row matching. We cannot say that look up data just like a database query, SQL query. We can't do that because there's no exact match. And that's where these mathematical model or machine learning helps us to still predict the right outcome for this type of unseen data. So this is the classification problem. Another type of problem in the machine learning that you usually come across is called regression. In the regression, you are given a set of features. That will be one feature. In this example, for simplicity, we are only taking one feature, carbon level, and we predicting the purity of air or purity of something, whatever. So we have a carbon level and then the purity outcome. So now your input features could be discrete outcome, could be yes, no, could be categorical input, could be a numbers. But the main thing is whether it's a classification or regression problem, to define a regression or classification problem, you're only going to look at the outcome variable. The outcome variable here is a continuous number. It's not a discrete outcome. It's not a categorical or outcome. It's a number. It's a continuous number. So when you have a continuous number as your outcome variable, this is what you're going to predict. This is what you need to learn to predict. Then it's called a regression problem. Yeah. So again, in this one, that's where the machine learning or developing these mathematical model helps us, because again, we can't query the data. We have this carbon level 1.32, and if we try to match it up, do we have any 1.32 exactly there? We have 1.36, but we have a higher value, we have a lower value 1.29, but there's no exact 1.32 in order to predict what going to be the purity for this carbon level, right? So that means we can't query the data, the existing data, to see what going to be the input. So our prediction could have those input data which our model have never seen before. And the idea is our mathematical model, where we have learned the y outcome based on some function of these input features, we're still able to very accurately predict the right outcome very close to the outcome, the actual outcome variable. So that's the classification regression, right? So you got to memorize this. What's the classification? When you have a categorical outcome to predict. Regression, when you have a fixed number, the continuous number to predict. That could be house prices you want to predict. You want to exactly predict the stock prices. You want to predict what could be the impurity level, the purity level, or what could be the drug concentration for certain type of application. So whenever you want to predict this continuous number, then it's a regression problem, right? Now, the idea is, if you have a simple, this kind of input data, input numbers, and you want to learn the outcome variable, which is also an outcome, which is also a continuous number. You know, in our high school or in a primary school, we used to make these plots where we used to make these dots on a plot for the x-axis and then matching y-axis, and then you fit a best fit line passing through most of these data points, right? And that line defines what's the relationship between an x and y, right? So basically, in this, if we only have two variables, and if one variable is going up, another variable is going up as well. So we see there's a strong correlation. So just knowing the relationship is not enough. That one increase of one variable also increases another variable. We need some kind of exact relationship, whether it's a straight line. And most of the people who come from a mathematical background, or who would have learned the mathematics at least until their year 10, they would know the equation of straight line is y is equal to mx plus c. And that's what we're going to use exactly here. So in this simple example, which in the machine learning terminology, it is called simple linear regression, we learn the relationship of y as an input feature x at a constant alpha plus beta x, and epsilon is our error. So this is exactly y is equal to mx plus y is equal to mx plus b, the famous equation of straight line that we have seen in our high school. So remember, m used to be the slope of line. So here instead we have this beta. So if we fit a straight line going through not very good with the drawing the line, so it should have gone from here. So then m is the slope of this line. In this case is beta, and then x is your input point, plus b is a y-intercept here. So where this line intercept the y, and then epsilon is the error. Because what's the error? I explain this in a moment. What's the epsilon? So because when we're gonna be predicting a new point on the line, so we have this one is our actual data point, and this one, the green one, is our predicted data point. So there's whenever we're going to predict a new point, so we might predict a new point here against an x value. The actual point might be here. So this is our epsilon, the error between an actual point and the predicted point. That's your epsilon. And in terms of overall error of this mathematical system, the way we calculate it, we calculate the difference between each of our predicted point. So yi is our actual data point. These the black ones here, and the predicted points are the green one, which are on this line. So you take a difference of these two and then you scale it. So why we scale it? The reason we scale it because we want to get rid of the negative number. So it doesn't matter whether the actual point is above the line or below the point, below the line. So you could have a positive number, negative number. So we're not interested in the signs. To get rid of the sign, we take it scale, and then you sum all these errors. So you take a difference here, you take a difference here, take their scale, take a difference here, take a scale, take a difference, take a scale, take a difference, take a scale, and then add them together. So you sum them, and that's going to be your sum of scared errors. So that's an indication of how good the fit is, like how good our model is. So the bigger the sum of scared error, the bad our fit would be. So to fit this straight line, we want to minimize the sum of scared error. So that's going to be where we have a minimum sum of scared error. So that's the best fit of this blue line. Now, in the regression, you give a continuous, you predict a continuous number. Now we have another type of problem, which is called logistic regression. So in logistic regression, we apply the linear regression of classification, but in a little bit different way. Why? Sometimes we convert a linear problem into logistic regression problem. For example, we can predict the exact value of a stock, what's going to be the stock price after 1 month, or what's going to be the stock price of Microsoft after 1 month. That's one way of prediction. Another way of prediction is we can say what's the likelihood of stock price going 1% up within next 30 days. So if the stock price goes up minus 1%, then that's your true label, that's your one label. If it doesn't, then it's your zero label. So you basically, in this problem, you want to make a decision whether you should go and buy or you should not buy a particular stock. So because the main decision is whether you buy or whether you not buy. Yeah, so that's why sometimes it's useful to convert a linear regression problem where you could predict a continuous number. That's not really helpful. The main decision that you want to make, whether you buy or not buy, right? So when you have this kind of problem where you have a discrete outcome, yes or no. So either you already have this discrete outcome to predict yes or no, 0, 1, or you convert a regression problem into this yes or no problem. That is called logistic regression. So how do you do that? We use the logistic or sigmoid function. What's that function? That function is a variant of our linear equation that we have seen before. Y is equal to mx plus b, or y is equal to alpha plus beta x. So that's the same thing. We use this alpha plus beta x and put the negative sign on here, and then put it as power of this e. E is a constant. We know its value is 2.75 roughly. You add it up to 1, and then overall you divide this whole thing by 1. So this is called the sigmoid function or logistic function. The benefit of doing this, like you're still using a feature x, you're still using the input, the same number. It's still going to give you a number, but the benefit of tweaking into this mathematical form, that you always going to get a number between 0 and 1. So that means you can apply this to any type of problem where you have to predict some sort of number. So whether it's a stock price, Apple price, which could be between like $100 to $200, or whether this could be a Google price, which is usually more than $1,000, or whether it's a Bitcoin price, which could be between 20,000, 30,000, or 50,000, or 100,000. So because in these type of problems where you have to predict a numerical outcome, and the number could be a huge number or number could be a very small, so then it's a very difficult for machine learning algorithms to learn a relationship and predict something useful. Instead, we do that very often in machine learning. We convert this problem into a number between 0 and 1. And if we convert this problem into a regarding its y outcome variable, the output variable, then it's called a logistic regression, right? So now in this situation, you will get a number between 0 and 1. Now you can, now whether you want to decide what going to be the output, the final output could be 1 or 0, you can come up with a threshold. In a logistic regression problem, the threshold is usually 0.5, simply. So if after this calculation, if your y output is greater than 0.5, then is yes, if yes or 1. If the y value of y is less than 0.5, then we predict the y is 0 or no. Simple, right? We can even convert regression problem into multiple regression problem, the logistic regression problem into multiple logistic regression by having many threshold. We could say if it's less than for example, 0.2, then it's 0. If between 0 to 3, it could be 1. If it's between 0.3 to 0.4, it could be 2. And from here is 3, from here is 4, from here is 5, from here is 6, from here is 7, right? So that means we can convert a linear regression problem into logistic regression between 0 and 1. And we can even extend this to multiple logistic regression where we could have many output classes. And depending on how many output classes you need to learn, you can define the thresholds, right? Is it making sense? Now let's quickly overview between the classification and regression. In the classification, we assign a class to each example, each row in our data. On the other hand, for the regression, we assign a numerical value for each row. In our classification problem, we have a output which is discrete or categorical value, whereas in the regression, our output is a continuous value, a continuous number. An example for the classification, as we've seen before, like whether we want to predict the tumor is there or not, or you want to predict the tumor is harmful or not harmful. For the regression problem, we've seen one example where we were predicting the purity. Another example could be predicting house prices or predicting the stock prices. Now, another important thing we need to know whenever we're doing some sort of data mining or data analysis task, we could have a biases in our data. The biases could be, there are many types of biases, but here I mentioned 4 most common type of biases. Very famous, one very famous example is under or representing a population. So in your data set, you might have all boys, right? Just example, or maybe most of the examples are male, very few female. So that means now your data has a biases toward the male participant. So you need to know that there is an underrepresentation of a certain gender, or it could be a racial or ethnic participation. We might be doing a study only on maybe British population or only on Pakistani population. So there are biases there. Now we could be training on the wrong outcome, right? We might might be training on the model accuracy rather than the business impact. For example, if you just trying to predict the stock going up or down, and if you focus on the accuracy, most of the time in such as environment which we have nowadays, the market is going down. So most of the time your stocks are going down and you can get that prediction right, but that's not very useful because your business not making any benefit out of it. They're not making any money. Your model could be 99% of the time accurate, but the main thing that you want to do for the profit of the business is ability to predict the stock that has a likelihood of going up, right? If the model is not achieving that, having a 99% accuracy doesn't make any sense. So we need to understand the business, and we need to see what sort of outcome our model need to learn. We could have outliers in our data, and that could affect how the model learns. We could have huge outliers, for example, and that could be an error in the data. we have heights of people, and we could have a few guys in there. One is 10-meter high, another one is 12-meter high, and that could be just somebody might want to write 1.2 instead that they're written 12-meter. Yeah. So so it's good to visually see the data and learn the data and see if there are some outliers, because they're gonna affect how the model learns. And we need to know, because the data that we are learning, we might be propagating the current state. So what do we mean by that? For example, you want to, and it happens in the Amazon. Amazon was using machine learning algorithm to recruit the people, and they were looking the best candidates, and their model learned from their existing data. So those people, their CVs, and what they ended up recruiting. So Amazon, most of the people working for the Amazon at one point were men. So the meta model only knew that the men could be the best person to recruit. So when you apply this kind of biased AI toward in the recruitment, so whenever the new candidates were coming in, the model was biased toward the men, so the model were choosing only men's and not the women's, right? So they picked up this problem, and then they fixed it. But it's important to know what sort of data do you have in your training, and if there are over under representations, or they just propagating the current state, knowing that very helpful, right? And we know the famous examples in America, where they were using AI algorithm to accuse people, and the algorithms were biases toward the black people, because the most of the examples that the AI have seen before were coming from the black people. So the AI algorithm was accusing black people all the time, and they were getting criminalized for that state. So it's picked up and then been hopefully fixed since then, but it was reported in the media. So we talked about a lot of bad things about the biases. So sometimes biases are not really a bad thing. It could be a good thing. The important thing is we need to know what are the biases, and whether it's a legitimate bias, or whether it's a bias that we don't want in our model to happen. So, for example, if our algorithm is biased toward predicting the likelihood of prostate cancer only in men, then that's a good bias. That's what we want, because we know the prostate cancer only happens to men, not to the women, right? And if our algorithm similarly biased toward the women, that they're getting ovarian cancer, that's good, that's fine, because we know that ovarian cancer is a woman disease, it's not a man's disease. So knowing a bias, and actually in some cases introducing a bias, in this case predicting the likelihood of getting pregnant, not pregnant, prostate cancer, ovarian cancer, which are gender related things, introducing these biases is good. Right. So that's my final thank you slide. Thank you for listening. That's my famous quote from Thomas Edison. Very famously, Thomas done lots of experiments to make the light bulb. And one time, one of the journalists asked the Thomas, "What did you learn?" So he said, basically, I learned 10,000 ways which don't make the bulb. So it's only one way to make a bulb, right? And it's a long journey that humans have gone through. This is a postcard from 1900, where they were looking into the future, and they're saying, like, the artist here depicted that maybe after 100 years we could have this type of robot, where the robot is doing the cleaning. We might be guiding them to do the cleaning, so the robot could be doing the homework for us. And here we are, after like 100 years now, we talking about AI basically taking over the world. Now we are worried whether AI will drive everything, and we might need license to do something. For example, now people are predicting that maybe not too far in the future, the AI will be driving all the cars, and if the humans want to drive a car, they needed a very special license to do that, because the humans are prone to accident, where the AI will have a very less likelihood of bumping the car into humans. We are a bit long way from there, but still there are serious talks happening, and seriously people are considering how the AI are taking over the world and what are the impacts. And that's why we have a whole new domain called ethical AI. Thank you very much for listening. And if you have any question, please feel free to ask.